Now, we've been comparing systems of linear equations to algebraic equations. This means that we've been comparing matrices to numbers. Now, there are similarities and differences between matrices and numbers. Numbers can be factored, and numbers have unique factorizations. For instance, 15 is 3 times 5, 21 is 3 times 7, and so on. These factorizations are unique. Matrices can also be factored. It turns out that matrix factorizations are not unique, and they also have various factorizations that have different uses. So in this section, we're going to talk about some useful factorizations, the LU, LDU, and PLDU factorizations. So these factorizations depend on how you break up the Gaussian elimination process. What we can do when we eliminate entries from a matrix is we can eliminate first all the entries below the diagonal, and that will end up with a matrix that is above the diagonal. In this way, we can write a matrix as a lower triangular matrix, which has non-zero entries below the diagonal and on the diagonal, times an upper triangular matrix that has 0 entries below the diagonal and only non-zero entries on and above the diagonal. Well, let's see how that works in a practical example. Here we have an original matrix M, and we're eliminating entries below the diagonal systematically. First, we eliminate the non-zero entries below the diagonal in the first column, then in the second column, then in the third column. That means we're going to eliminate first this entry, non-zero entry below the diagonal in the first column. Then we'll eliminate this entry, non-zero entry in the second column below the diagonal, and then we'll eliminate this entry. And you can see what we've done now. Now we've actually done 3 row addition operations. Here we've actually added 2 times the first row plus the third row to get this one. To get this one, we've added the second row to the fourth row to get rid of this one. And here we've added the third row to the fourth row to get this one. Now those 3 operations that I mentioned, E1, E2, E3, have corresponding elementary matrices, which we see here. Right. And these matrices have inverses because every elementary row operation can be inverted. And I mentioned that adding 2 times one row to another row is inverted by subtracting 2 times that row to the other row. So you can see the nice pattern of inverses. Here the off-diagonal entry is +1. Here it's -1. Here the off-diagonal entry is -1. Here it's +1. Right now, we know that E1, E2, E3 in reverse order affect the 3 row operations required to make M into an upper triangular matrix. So here we have this upper triangular matrix is equal to M with first E1, then E2, then E3 applied on the left. Now, just by comparison with ordinary algebra, in order to solve for M, I multiply both sides by inverses. If I multiply both sides by E3 inverse, that will remove the E3 on this side. Then if I multiply both sides by E2 inverse, that will remove the E2. When I multiply both sides by E1 inverse, I will remove the E1 and I get M here. The order is important. In ordinary algebra, the order is not important, but here the order is very important. You have to multiply E1 inverse, E2 inverse, E3 inverse in order to undo E3, E2, E1. Notice the reverse order. Right now, each one of these elementary row operations is a lower triangular matrix. So we've got 3 lower triangular matrices operating on an upper triangular. So we've written our original matrix M as 3 lower triangular matrices times the upper triangular. These 3 lower triangular matrices multiply together to give a lower triangular matrix. Only the entries below the diagonal are affected. Right, so our original matrix M now is expressed as a lower times the upper triangular matrix. This lower triangular matrix corresponded to the process of removing all entries below the diagonal And then what was left was a matrix whose entries are above the diagonal. All right, so here we have our LU decomposition. All right, now we can go a little bit further. Here we have a matrix which is upper triangular, but notice the difference between this one and this one. This one has 1s on the diagonal. This one doesn't have 1s on the diagonal. So what we can do is decompose this one further into a product of a matrix that has only diagonal entries times a matrix that has only 1s on the diagonal. So let's work further with this upper triangular matrix and get another decomposition. All right. So here's the upper triangular matrix that was obtained by removing the lower diagonal part. And we're going to make the diagonal entries 1 systematically. First by multiplying the first row by 2, then the third row by 1/3, then the fourth row by minus 1/3. And that will give us a matrix that has 1s on the diagonals. So we've done that by multiplying by 3 elementary row operation matrices. The 3 elementary row operations are here. This one multiplies the first row by 1/2, this one by 1/3, this one by minus 1/3. Okay. They have the corresponding inverses, right? The inverse of multiplying the first row by 1/2 is multiply the first row by 2, and so on. Right. Now, I've already got 3 elementary row operation matrices to give me my upper triangular matrix. Now I have 3 additional ones. And I have to multiply them in reverse order in order to get this result. Okay. So the final result that I get, if you notice, the final result that I got here has only 1s on the diagonal. Okay. So I've reduced my first matrix to a matrix that has only 1s on the diagonal. To recover the original matrix, I just do my elementary row operation matrices inverses in the reverse order. And I group them this way. These were the lower diagonal operations. These were the diagonal operations that gave me 1s in the diagonal. So this product of 3 inverse elementary row operation matrices is here. This product of diagonals is here. And then I get the product of 3 matrices, which gives me my original matrix. Lower triangular, diagonal, upper triangular. This is a LDU factorization. Now you may wonder, what's the big deal about this LU and LDU decompositions when we already know how to solve linear equations? Well, it turns out that when you implement solution on the computer, LU is the way to go. You can see that in your numerical analysis class when you take that. So it is very useful. It's also interesting to understand what the process is really doing. All right, so so far we have not done anything with row exchanges. Now if we have row exchange, then we throw something else into the mix, and we end up with a decomposition called PLDU. So here's an example that shows how that works. If I start with this matrix here, this matrix has a 0 up here. Now I want to get a pivot up here, so I want a 1 here. The easiest way to get a 1 here is to switch this row out with a different one. And I typically want to do that first. So if I switch this row out with another one, that means, for instance, I can exchange the first 2 rows. And that corresponds to this ERO matrix, where I've switched the first 2 rows of the identity. Now this matrix is its own inverse. So in the row reduction process, first I do this row operation where I switch the first 2 rows, then I do all the other ones. All right, so the P comes first, and then E1, E2, and so on. Now when I unzip those and run those backwards, as we've seen before, we can recover our original matrix by taking the inverses of these matrices in reverse order. The P is first. P inverse is the same as P. And then these are my L operations. These are my U operations. I'm sorry, these are my L operations. These are my diagonal operations. And this is the U that I end up with. I'm sorry, this shouldn't be an I here. This should be a U because I end up with a U. All right, so I start with the U I end up with, then I undo all of the operations this way, and I can write this matrix product as a P times a L times a D times a U, and that gives me my original matrix M. I have my PLDU decomposition.